I'm really very glad that this lecture series between CMSA and Tsinghua is still going on. We started it a few years ago. It did very well, and I'm very happy that it's still going on well. Except our relation between America and China are not doing as great as what we used to. But I'm glad that academically we are doing fine. And I'm very proud to see this title of Scott, Survey Sum and Euclidean Lattice Young Mills, a subject that I always admire, and Witten always told me how important it is. So I'm really glad that I can listen to this talk. Thank you.
Thank you. Should I start? Yeah. Okay. It's wonderful to be here. Also, hello to all my friends in China. I'm talking about surface sums and Euclidean lattice Yang mills. So Euclidean lattice Yang mills is a pretty simple thing to describe. You just imagine you have a grid of some kind, and what we're going to do is assign a matrix to every directed edge of the grid. And the matrix will be such that the matrix you assign for one directed edge has to be the inverse of the matrix you assign to the inverse of that directed edge. So that's the one constraint you have. Other than that, you have a matrix value degree of freedom for every edge. And typically we restrict the matrices to some particular group. In this picture here, it's sort of the group of 90-degree rotations and reflections. So these are all just 0, 1, 2 by 2 matrices. But usually in the physical applications, these will be compact Lie groups. So think SU2, SU3, or UN, for some large n, sometimes ON, some sort of compact Lie group. And usually you start by using IID Haar measure on each edge. So imagine you independently choose Haar measure for every edge to choose a matrix there. And then you want to put in a weighting that makes the product of the matrices around any small square want to be close to the identity. So there's sort of the simplest story you have maybe is the Ising model, where you have an object on every vertex, like a spin, and you have something that makes neighboring spins want to be compatible. Here, this is the next simplest thing, where you have an object for every edge, and then you want to have the edges around a square be compatible. And compatible would mean that the product around them is equal to the identity. You could think of it as sort of a connection, in the sense that if I give you any path, you can multiply the edges along that path, and that will give you some sort of a group transformation. And when you say the product around a small set of things is close to the identity, that corresponds to what we call a flat connection, meaning if you go around a loop, you come back to where you started. So in order to put in this bias to make the connection want to be flat, simple in this way, one way they do it is they say we're going to weight by the exponential of beta times the sum of the real parts of the plaquette traces. So a trace, for every square, you can take the trace of the product of matrices around that square. And because it's a trace, it doesn't, these are compact Lie groups. So the eigenvalues will all be roots of unity. So they're all just, complex modulus 1 values. So the real part of the trace will be the same for the matrix and for its inverse. And it's also the same doesn't matter which point you start when going around the square, because it just changes it up to conjugation, and that doesn't affect the real part of the trace. So real part of trace is kind of a natural thing to find for every plaquette. And when you take the real part of that, that's going to be larger when the matrix is close to the identity, because you think you have all roots of unity. And so sort of somehow locally speaking, your distance from the identity, somehow the real part of the trace is somehow growing quadratically in your distance from the identity as you sort of move your eigenvalue off the identity. And so when you do this way, it's kind of, think of it like locally, it's like this sort of a Gaussian a quadratic force sort of pushing you to want to be closer to all your eigenvalues being 1 and paying you some price when you deviate from that. Okay, so that's what the model is. So a Wilson loop is, you take any big loop and you multiply the product of matrices around that loop and find the expected trace. And so a problem is sort of understand and construct a continuum version of this theory. Is there some sort of limit where you take the mesh finder and somehow describe some continuum story? Well, this is well known here around Harvard, because of the Clay Institute and Glim and Jaffe, who did a lot in constructive field theory early on and helped pioneer this field and this question in particular. So they famously promised to give $1 million to anyone who could construct a continuum version of the theory I just described and explain some of its basic properties. So basic, and it's very important to solve this problem quickly because the prize is not adjusted for inflation. It may be getting worse soon. So think of lattice Yang-Mills theory as a simple statistical physical model like the Ising model, and we will understand something about the limiting model you get when the mesh size tends to 0. So there's been tremendous success in recent years for the Ising model, things like that. We understand that far better now than we did 30 years ago. And the goal is to sort of repeat the success for the next simplest model after the Ising model, which is this Yang-Mills type model. And if you want to give a credible construction of the continuum limit, even if maybe you can't prove right away that the lattice converges to it. So for comparison, when Oded Schramm was thinking about Ising model interfaces, he constructed what we now call the Schramm-Milgler evolution, this particular family of random fractal curves, as a possible limit. And it was only later proved by Smirnov and others that the Ising models converge to this. That when you take the interface in the 2 dimensions between the plus and minus spin regions, you get these beautiful curves. And so he was able to prove this for a grid with a number of collaborators. And but the construction of SLE itself preceded that by some years. And similarly, if you look at this, what we call Liouville quantum gravity, this model for random surfaces, we now know that in various senses, this is a limit of the natural discrete random surface models, random planar map models. But the construction of this as a mathematical object, or at least in sort of a physics sense, maybe with not complete math rigor, kind of preceded the proof of the scaling limit result by decades. So it took a long time from the basic idea of the construction before we started actually be able to prove some sort of things about the limit. And so I make this point just to maybe point out that if you want to win the $1 million, you don't actually have to prove that the lattice model converges. You just have to construct the continuum object. So you might think of the lattice model as a tool for constructing the limiting object, or as just something that guides your intuition, gives you a clue for how you might go about it. Okay, so there are different approaches to trying to attack this continuum model. So you sort of want to assign an expected trace to each maybe nice enough continuum directed loop. Maybe there's going to be some generalized function sense where you make sense of this. And there are different approaches they've had to go about this. So the one is the SPDE approach. And so this is, well, you try to construct a dynamical version of this Yang-Mills process. Maybe on a torus, you take the initial value to be what we call a Gaussian free field connection, sort of a simple Gaussian field. And so somehow each coordinate direction, you kind of have an independent Gaussian free field, deciding what it takes values in some Lie algebra, say. So this is kind of a Gaussian connection that is supposed to be the correct model at small scales. And then you sort of hope that if you can construct this dynamic process, that the other scales will mix in time. And so this kind of builds on techniques, including Martin Heyer, Hao Shen, Sky Calville. Just a few of the names are using this approach. You probably know Martin Heyer won a Fields Medal for work sort of in this area, regularity structures. And the idea is, if you can apply this to Yang-Mills, you can construct a dynamical version and try to understand maybe what's going on. So if you could construct a continuum dynamical version and run this thing and show that it is well defined for all time, then you could maybe hope to show that even if you start with a Gaussian random field, that over time it will mix, and that the long-term limit will be this, the stationary measure of this object will be the object you want. So it's a kind of an interesting approach because it somehow attempts to do something harder, something we've not managed to do for Liouville quantum gravity, for example, which is to construct the right continuum evolution. And so instead of saying, first we'll construct stationary and then go to the dynamics, it's sort of, we'll start with dynamics and then use that to construct the stationary. Which may sound like it's a lot to do, but there has been amazing progress in 3 dimensions. Namely, they've been able to show that if you start with the Gaussian free field, the dynamics is well defined for a positive amount of time. So they can't show that it goes on for infinity. They can't show it converges to a stationary distribution. They can't show that distribution is unique. You know, there are lots of work left to do. But the fact that they can get this thing started at all and show this thing is well defined at all is considered a huge breakthrough. But that's tremendous progress. But that progress so far is only in 3D. 4D, this approach seems to be somewhat, we would really need even bigger new ideas to make progress in 4D. Other approaches you could try to, well, you know, also we'll start with the Gaussian field and modify the field in some way in the continuum and try to take some sort of limit of that. So it's usually in this case, there are a million ways to construct an approximation that you think converges to the limit. It's very hard to prove something converges to a limit, and that the limit has the sort of same symmetries that all the symmetries you want it to have. But I'm going to focus today on this lattice approach, where you try to really use the lattice version to give you intuition, and use the lattice version to maybe at some point be able to even take a limit and prove things about this limit. And so, warm up. So we all, maybe if we know a little bit of statistical physics, know that there are various random collections of loops you can describe. So there are ways to make a model where you get some random collection of loops. Maybe this is, you run a percolation on a hexagonal lattice and you have boundaries between the plus and the minus, you know, or the black and white regions, or 2 different colors. Or maybe you take 2 diamond models, put them on top of each other, and that forms some collection of loops. And so you get some interesting random collection of loops. There are even models where maybe the loops are allowed to intersect themselves. You get some sort of collection of Brownian loops. But in all of these models, you can do something interesting, which is that you say, well, instead of saying, you know, at every vertex it has to be connected to an even number of edges corresponding to loops going in and out, maybe we take 2 vertices where we allow them to be connected to an odd number, or to maybe just 1 in this example. In that case, there's going to be like a special path that goes between those 2 vertices, x and y. And so we call this putting a defect in the model. You've inserted this path, this pair x and y. And you might ask, what is the insertion cost? So in some cases, you can compute a partition function for this model and a partition function for the original model. And the partition function for this model is smaller. You can say that there's some sort of a cost to putting in those 2 vertices. And maybe the log of that cost would be some sort of measure of, you know, how much energy it takes to put in these 2 points and how much energy it would take to pull them apart even further. And in some models, the ratio of these 2 partition functions decays exponentially as x and y get further apart, exponentially the distance between x and y. And in some models, it will decay polynomially in the distance between the 2. And in those cases, sometimes this, you know, in the first case, maybe the path will approximate a straight line. In the second case, maybe it approximates an interesting fractal curve, like an SLE curve. So there's sometimes a phase transition where if you tune parameters correctly, you can constrain sort of a hybrid model, something sort of on the interface between the 2 things. Then we have a model that looks like this, you know, the curves look like SLE. It looks like this sort of model at small scales with this sort of fractal structure polynomial. But then on large scales, it looks like this exponential decay of correlations. So they would sometimes call this an off-critical model, or they say that they sometimes use the word massive model for the exponential decay case and say, well, you have mass on large scales, but it becomes massless on small scales. That's vocabulary that's sometimes used. Don't worry about what it has to do with mass. It's used in normal English parlance. Here's a example. So here's a double dimer model where I have a domino tiling sort of a chessboard. So somehow each I group together the black and white squares into pairs. And so I've sort of drawn in red whenever two things are, it's sort of a perfect matching on this graph of squares. And then I do another perfect matching in blue. And you can see I have two squares where there's a defect. And the defect means that no blue is allowed to use that square. So the blue will be a matching of the complement of the green squares. The red is a matching of something that includes the green squares. And now when I put these things on top of each other, I get a bunch of loops. So delete the colors, I get a bunch of loops and this one special path. And this dimer model is a case where we actually understand things very well. We understand the phase transition. You can put periodic weights on the edges, making some edges preferable to others. And there'll be some lovely phase transitions where for some values, you'll be in this kind of exponential decay of correlations. You really pay a high insertion cost as you move these things further apart, exponentially growing. And then there's this other case where you'll have this kind of polynomial thing, and should get these SLE type curves. Okay, so what happens if you want to generalize that story one step higher? So let's say we're going to go from Ising model to Yang-Mills. Well, we're going to go from these random curve models to what's the next simplest thing? Well, the next simplest thing would be you have closed models of random surfaces instead of loops. So you have a collection of plaquettes that are glued together on edges, and they make a collection of closed surfaces. Maybe the surfaces are non-intersecting, maybe they're intersecting, but there are lots of models for constructing collections of surfaces like this. And then you can ask, what happens if I put in a loop and I require that along that loop, instead of having an even number of plaquettes coming together and forming the surface and glued together, you have an odd number. And or maybe just one in this case, I have these things meeting up like this, and so there's going to be some surface that spans this as its boundary. Maybe it's a homogeneous surface, maybe you're simply connected, but you have some spanning surface of this thing. And you can ask similar questions like, what is the insertion cost? So in some models, if you can take the ratio of the partition function over here to the partition function over here, and in some models that ratio will be decaying exponentially in the minimal area spanned by this loop. So somehow maybe these surfaces, they want to all be really, really small, and when you force there to be a big surface, that's sort of really expensive, and you pay a price which is exponential in the area of this big surface. So that's something you can imagine happening. But you can also imagine a story where it doesn't happen, or maybe the price is just exponential in the perimeter, the boundary length, or it's something in it's exponential in the or maybe it's just decays polynomially in the diameter of this thing. You have some sort of different order of decay. And then you could ask, what does a typical surface look like? So in this case where you're paying this price exponential in the area, maybe the surface wants to be the minimal area surface. So it approximates minimal area, and maybe over here, the surface is something wild and crazy. Maybe it's some sort of space-filling surface that just happens to match up here on the boundary, or maybe it's some kind of weird fractal surface you can ask, or it's a tree-like thing, infinite diameter. There are all sorts of things you can imagine happening with this random surface. And you can imagine if there's a scaling limit you could take where you get sort of some hybrid. You maybe want a model that looks like the massive case, strong, high insertion cost case at large scales, and maybe this low cost at small scales. Okay. And so, in the dimer model, we have what we call a rough phase for certain choices of parameters. The whole path is supposed to look like a fractal curve, SLE4. There's something called a surface tension, which is locally quadratic. That's sort of the price you pay if you want to have sort of there's a height function for these surface models. If you want to put that in a different slope, you pay a price depending on the slope. And you can ask, as you put in these defects, how does it decay? And here it's going to be, sort of the energy is like minus log of the distance. And you'll have an expected height function, that is going to be harmonic. So you have all these kind of nice things that behave related to the Gaussian free field. And in the smooth phase, the path will be a straight line. The surface tension will have a cusp. You'll have a defect in your partition function. You'll have an exponential decay you'll pay for moving things further apart. And your expected height function is going to have a jump. You know, when you put in this defect, you'll have a multivariate height function. When you go around the loop, you sort of jump when you cross this sort of line between the two defect points. And we can construct this off-critical model called the Weingarten model, and we know not everything about it, but quite a lot about this sort of intermediate model, where you get something that's Gaussian on small scales and looks like a massive field on large scales. So the goal is to somehow extend this success to these random surface models, which are closely related to Yang-Mills. Okay, so let me maybe skip this ahead for now and go straight to say a little bit about what we've done. Well, no, maybe let me just go back here to the picture and I'll say what we've done in words here. So, I mean, what we've been doing is analyzing ways that you can actually represent the Yang-Mills Wilson loop expectation. So, you know, the expected product of trace when you multiply all this matrices around a loop in a Yang-Mills model, that it turns out to be equivalent to the insertion cost of a loop in a related random surface model. So we have this recipe that's, you know, we've worked on in the last few years, and it sort of builds on other work doing what they call gauge string duality over, you know, decades previously. And it's a story that tells you that basically lets you convert this hard problem in Yang-Mills theory about understanding these Wilson loop expectations to a hard problem in random surface theory, which is, you know, understand the, you know, for these certain kind of tricky random surface models, whether you have the insertion cost is growing like the area or something else. This is, by the way, this area law in the physics term for this is quark confinement. And when we talk about exponential decay of correlations, the physics term is mass gap. And so they sort of translated these into sort of probabilistic language. And I'm not going to explain the whole process by which the translation occurs, but you can just interpret it as that's what these words mean. So quark, you know, quark confinement means you have this exponential price you pay in the area. All right. Okay, and so now you know, the idea is you want to sort of construct this model, this sort of limit of these random surface models that will have somehow the quark confinement behavior and mass gap behavior that you expect it to have. All right. So maybe I'll just say there are a lot of problems you can ask already about the Dimer model. So I've got people here like Amol here in the audience, and people here who know Dimer models very well, who I'm very happy if they can, you know, help me address some of these problems just already in the 2D Dimer case. You know, what happens if you put negative weights on some of the edges in the Dimer model? So it's not strictly a probability model. It's something where, you know, you're summing over weights that can be positive and negative, but you still want to ask about the analog of insertion cost. You know, can you still do these things even for the Dimer model? Can you understand the 3D Dimer model where you get something more like an area law story or you know, a similar sort of phase transition between area and not area law? Can you extend the Weingarten model to 3D? Can you do analogs for what we call the surface tension? So I'm just going to toss these up here, but there's a whole bunch of questions you can ask already in 2D, just about dimers, where the better and more satisfying an answer you get, the more confident we are that we can extend that answer to this four-dimensional case with random surfaces where we're working at the moment. So the recent papers we've had on this subject, I want to say there's one called Wilson loop expectations as sums over surfaces on the plane, where we were really able to, let me go back, we were really able to understand this theory very well in 2 dimensions. So it turns out that Yang-Mills theory is much easier in dimension 2 than in dimension 3 or 4. And it seems like it might be much easier in 3 than 4. 4 is what we really care about. That 4 is the big prize. 2, there are many things, something called gauge fixing, that actually let you simplify the model tremendously. And that makes 2 dimensions a nice test case for any sort of techniques you think might work in 4D. If you think it's going to work in 4D, you first try to make it work in 2D. So these people doing the SPDE theory, a lot of them have worked very hard on just understanding the 2-dimensional case to death. Even though we sort of already felt we understand it perfectly, they want to understand it from this perspective, and this perspective on this perspective, just to see that there's a proof of concept that these other tools might actually work. And they've had a lot of success in showing that these different things work in 2D. But one thing you can do in 2D is draw a very complicated, funny-looking loop, and maybe a loop that intersects itself a few times, and ask, what is the expected Wilson loop trace for that sort of funny loop? It turns out if it's a simple closed loop, the answer is very simple. It just like decays exponentially in the area of the loop. So it's very easy to prove that in 2 dimensions. But if it's a funny loop, well, then it becomes like a slightly trickier problem in random matrices. And you could convert it into a random matrix problem. But we were able to show, a recent paper by Terry Levy, the asterisk in 2017, managed to show in the n equals infinity limit, give like very explicit formulas for what these Wilson loop traces would be. In the big N, N is like the matrix of a Lie group, like SON, SUN. So when the matrix group goes to infinity, they were able to understand these things and give very precise formulas. There's this beautiful chart showing for all the different types of loops what the expected Wilson loop trace is. And what we were able to do in this paper was extend that chart to finite n, which is important because in the real world, that's the finite n, that's the case we care about, SU3, SU4. And we were able to extend that whole story to finite n and build our own lovely table. And if the formulas become more complicated, they can call Gaussian, Sinch functions, and they're longer, but they're still, you can write these things down and say explicitly what they are. But even more interesting to us than this explicit formula was that we were able to understand it in terms of sums over surfaces, and show that in some case, there is some sort of maybe, if I give you a loop that goes around and maybe intersects itself one time, you can try to think what sort of surfaces have that loop as its boundary. And it turns out that in our story here, you can sum over just the minimal area surfaces, somehow the locally flat surfaces that have this thing as its boundary. And those things will usually have a finite number of ramification points. And so if you just integrate over all the sort of possible locations of the ramification points, and then assign some weight that depends on the genus for each of these things, then this actually gives you the right answer. So we really are able to prove that the sum over surface tool actually works the way it's supposed to in 2 dimensions, which is encouraging if you hope to someday do something similar in higher dimensions. This other paper, next to random surfaces, lattice Mills, which we really understood in the lattice models, how you could explain the Wilson loop expectation as a sum over surfaces that have that model as its boundary. And so we came up with some sort of surface model, and we're able to kind of rigorously show this statement about the insertion cost. If you put this big loop, the insertion cost in our random surface model is indeed the Wilson loop expectation in the Yang-Mills model. And it turns out it's connected to Weingarten calculus, a whole bunch of very beautiful stories in representation theory. And so it's a very deep, wonderful topic. And so, if you read the paper, it has like 20 open questions or something where I think that gets started. There's just a lot of kind of very interesting things you can try to work on. Next, we have this paper called Fractional Gaussian Forms and Gauge Theory, an overview, 2024. And this is where we focus just on the Gaussian case. So you can imagine, think about what happens if you make this force really, really strong that makes the plaquette things want to be close to the identity. So basically, you make it so strong that, around any plaquette, you multiply the edges with very high probability. It's just like the identity plus you can think of some infinitesimal Lie algebra element, something very small. And when the matrix is that close to the identity, the matrices approximately commute. So when you multiply two matrices, one is identity plus tiny element A, one is identity plus tiny element B. You multiply them, you get identity plus A plus B. Plus a very smaller order term after that, right? So locally, it's going to look very much like it'll look abelian. And when it's abelian, and this force will start to look really much like the quadratic function, like I was describing before, and it starts to just look like a Gaussian field. And so when you get this really strong force, it starts to look like Gaussian, and you can understand it because we understand Gaussians perfectly. But even for Gaussians, trying to kind of say, okay, I give you this Gaussian field, how do you make sense of the limit? It'll be some generalized function. What sort of test functions can you integrate against? What sort of loops? Maybe for a single loop, it's not defined. But if you take an average over a family of loops, it's well defined. And so you get something which is what we call a fractional Gaussian form. And it's related to what we call fractional Gaussian fields. And you can talk about, what's the curl of these things? What's the inverse curl? What you can put to curvature. You can do various operations. And just like explaining the Gaussian case perfectly, this is already a pretty long paper, but it's fun because you can read it and feel like you actually understand something well at the end. Whereas most problems in quantum field theory, they're kind of too hard to understand mathematically rigorously. And so you just have to understand bits and pieces. You never really quite get everything. Here, I say, spend a couple of weeks on this, you'll know it perfectly. You'll be the complete master of the fractional Gaussian forms. And so that, was kind of a fun paper to write. And it's interesting, I want to say that in this Yang-Mills story, somehow we understand very well what happens, as I say, when you have very strong force and it really wants to be close to the identity. We also understand very well what happens when you have very weak force. And so it has the force making it want to be close to the identity as you go around an edge is very small. So in that case, we can very easily prove that you have this kind of area law property, the exponential decay as you get larger. Things are much easier to prove in that case. There are certain surface expansions that converge much more easily. And so, so there's this weird story where we can understand one extreme and the other extreme, but the stuff in the middle is what's giving us trouble. And in order to construct this sort of off-critical limit, what we really want is something that's almost at the very strong force extreme. So you have the Gaussian, we want to go a little bit off the Gaussian in order to come up with a model that looks Gaussian at small scales, but non-Gaussian at large scales. And so you want to take a finer and finer mesh, but as the mesh gets finer, this sort of force gets stronger and stronger, and get some sort of limit that is this sort of hybrid between Gaussian and non-Gaussian. So I'll say, upshot, summarize these papers in a written sentence. In the lattice version of the famous Yang-Mills problem, the so-called Wuest loop expectation of a loop L is equivalent to the insertion cost of L in a related random surface model. Some parts of this theory are classical and some are new, and there are various parameters, beta, which is this strength of the force, making you want to be close to the identity, big N, which is the dimension of this matrix group, and then your mesh size and what type of loop you take, and you may expect different types of scaling limits depending on which part of this space you program. If you take n goes to infinity, or if you take n fixed and take, so let's say the Gaussian field is already one type of scaling limit, but there are other types of scaling limits that you can hope to get. And there's a certain duality. We represent big N as somehow the group size and beta as the inverse temperature. But it turns out that when you do this conversion to a random surface model, the roles of N and beta actually swap. So in this duality picture, we'll find that this big N will represent something like inverse temperature, and this beta will represent something like the size of a group. And somehow the number of Plycat edges to be assigned using a symmetric group element. So there's this weird swapping of roles as you go from. And when you try to take a limit, it really depends on how you scale these parameters. So for example, if you take this big N goes to infinity, this is called the 't Hooft scaling. It's been sort of known for a long time. In that case, it somehow corresponds to making your surfaces want to be simply connected. Or, if you don't fix let n go to infinity, you may get very high genus and kind of space filling things. So you might think the scaling limit is not going to be a surface at all. It'll be more like sort of a random two form. That may be the right way to think of what a limit of this object would be. Maybe some Gaussian, some hybrid permutation, the various ways of thinking about what the limit might be. And so that all these these papers have a long series of open problems. And so particularly the surface sum for Lattice Mills is by three of my colleagues who are in our group at MIT now. So this really handles the large n limit and shows that this whole idea of having it a sum over simply connected surfaces works out very nicely and neatly in that case. And many things simplify in the large n limit. Okay, so if you've heard about this story before, probably some of the names up here are familiar to you. So this goes back all the way to 70s, for people who understood that there should be some sort of a connection between sums over surfaces and these matrix group, expected traces of random matrix group elements. Maybe in this Yang-Mills setting, or maybe even in simpler settings where you just have a single random matrix. And so this is very far from exhaustive list, but let's consider the simple story. Suppose I sample A from n-dimensional Gaussian unitary ensemble. Okay, so this is the model where basically you choose an independent complex Gaussian random variable for every edge of your n by n matrix group, except then you project onto the space of Hermitian matrices. So basically, when you take the conjugate, you'll have this symmetry. If you know Aij, Hji, and it'll be real along the diagonal. Otherwise, that is just independent Gaussians. So it's kind of one of the simplest models. For me, they call it unitary, not because the matrices are unitary, but because it's invariant under multiplication by a unitary group element. And but this is a Gaussian matrix. So this is different from a hard measure on a compact Lie group, but it's a very simple random matrix thing. And I ask, if A is this kind of random matrix, how would you compute the expectation of the trace of A to the fourth times the trace of A to the sixth times the trace of A to the eighth? Now, how many of you know how to compute that already? Okay, just gauge my audience. So at least two hands come up, people who are very happy with this computation already. Okay, for those who don't know, it's time you knew, and this will be your day to learn. So I imagine that every term of this trace, every term of this trace A to the fourth has the form I can write it as expanded as Aij, Ajk, Akl, Ali. So these are basically when you, I guess you guys know how to multiply matrices, right? If I multiply 4 matrices, then and I want to know the Ij term of the product, then I just sum over all the ways I can put in these intermediate values, where it's Jj here, Kk, and so on. So, and here I'm only considering it's I, the same index on one end and the other, because I'm taking the trace. So for each, if I fix I in the boundary and sum over the Jk and L, that would give me one element of this product of 4 matrices, and then and now I'm summing over the diagonal, and so I'm just going to sum this over all possible Ijkl pairs. Okay, so if I have n, if this is an n by n matrix, then I have n to the fourth terms like this that I'm summing over. And so I'm going to represent a single term like this by a directed square, and you'll see why in a minute. It'll be a directed square with vertices labeled I, J, K, L. So it tells me the cyclic order in which these things appear, and I'll have one directed edge for each of these 4 factors. I'll do the same thing for A to the 6th and A to the 8th. I'll get a hexagon and an octagon. And so here's the picture. So if I take a single term of this, like A21, A13, A32, A22, that term will be described by this picture. So I'll draw in dark the starting place, the 2, this circle. So it's 2 to 1, 1 to 3, 3 to 2, 2 to 2. And so then I have a term over here and a term over here. And so basically, when I want to compute the expected trace of all these things, I have to sum over all of the n to the 4th choices for this, times the n to the 6th choices for this, times the n to the 8th choices for this. Each one of those choices gives me something, and now I have to compute this expected product. Okay, but now we have to do this expected product. So how many of you here know Wick's formula? ISO's formula? Okay, not everybody, but a much larger percentage than knew how to compute that expected trace product initially. So Wick's formula is this very simple thing. It said that you want to compute the expected expectation of a product of jointly Gaussian random variables. And then what you do is you look over all of the ways to divide those Gaussian random variables into pairs, and then you look at the expected product for each of those pairs, and then you multiply those expectations. So anytime you have a centered collection of Gaussian random variables, they all have mean 0. You have this nice description. So basically, if I want to compute the expectation of just this one term, I mean, it's kind of a crazy thing, right? So we started out with n to the 4 plus 6 plus 8. So n to the 18th guys. And now for each one of those 18th guys, n to the 18th guys, I'm going to expand that in saying that I sum over all the ways of grouping 2 of these guys into pairs. Maybe this one, this A13 matches with this A14 over here. This A12 matches with this A32. And I look at the expected products over those pairs, the product of all those pairwise expectations. And then I sum that over all the terms, and that gives me the overall expectation. So, but something interesting happens here is that if I pair the A11 with the A53, what's the expected product of A11 and A53? 0, that's right, because these things are independent. And in fact, what's the expected product of A14 times A14? It's also 0 because this is a complex Gaussian. And if you take complex Gaussian and you square it, you still get something that's rotationally symmetric around 0, and so its expectation is 0. But what if I take the expectation of A14 times A41? Well, that should be 1. Depending how we normalize things, that'll just be 1. The expectation of A11 times itself will be 1. So basically, in order to get a non-zero element, you have to match these things together so that each thing A14 gets matched to, say, an A41, something with the opposite sign. And the way you would think about that is if we view these terms as directed edges here, I have to glue the 1 pointing to 2 to something else where it's going the opposite direction, like it's a 2 pointing to 1. Which basically means, I can think of the way that's working is that I'm sort of gluing this thing in an orientation, I glue an edge pointing this way to an edge pointing this way, but I require their endpoints to match up. And so we think of it as saying it's an orientation preserving gluing that is compatible along the vertices. Okay, so now I look at all ways of gluing these things together to make a surface, and I can do something interesting. So I say, let's imagine I first tell you what the topological shape of the surface is, and then I decide what the labelings of the vertices are. So because somehow we're counting the number of, I told you this expectation is just a count of the number of labeled surface orientation preserving surfaces we can make out of this thing. And so, but the thing is, when I make a surface, the number of vertices is not fixed. So the number of faces is fixed, that's always 3. The number of edges is fixed. But the number of vertices can change, and because of that, it means it changes along with the genus of the surface. So you have this Euler characteristic, like faces minus edges plus vertices. That's going to be something that changes depending on this genus. And so so what you end up getting is n big summing over all surfaces you can make of big N to the number of vertices, which gives you the set of possible labelings. Okay. So this, maybe if you got nothing else out of this talk, you at least learn this classical story that goes back, several decades, which gives you the first glimpse of why something about expected traces of random matrices should be equivalent to something about these random surfaces, sums over surfaces. Well, okay, so that's the story. So it's Wick's theorem. And I'm just putting here up on the screen everything that I just said to you in words. So finally, this expected trace at the end, it's a sum aj n sub j, where a sub j is the number of surfaces with j vertices. So now this problem boils down to a problem about counting the number of surfaces you can make of different types. Okay, and there's a similar story for, say, Gaussian orthogonal ensemble, where the maps become orientable, weights are not signed, there are lots of variants for different groups. Okay, if I do E to this, to the trace, then I could get a formal like Taylor experience where I get surfaces of various sizes. But I can also think about more than one matrix. But here, you can imagine that I have 4 matrices. I'll label them R, O, G, and B for red, orange, green, and black. And now if I want to do a product like the one that showed up there with some word in these crazy colored matrices, then I can represent an element in the expansion of that product, same way as before, except that now each of these edges comes with a color. And now when I sum over gluings, I have to glue a color to something of the same color. Otherwise, I get 0, because these matrices are independent of each other, one matrix to the next. So in order to get a non-zero thing, the colors have to glue to each other. So now I'm summing over things that respect the color. Otherwise than that, it's just the exact same story as before. All right. And I guess maybe the story I want to, I'm going the wrong direction just a minute. What I want to make is, if you want to do Lattice-Yang-Mills theory, then what you do is you can imagine constructing a different color for every edge of your lattice. So you have some grid, ZD, and every single edge comes with a different color. And then you start out by putting in a whole bunch of these plaquettes. And so if you weight by the product of the traces of those plaquettes, that gives you a bias based on those individual plaquettes. And then you can put in a whole bunch of these small plaquettes and maybe one big loop. And then you want to ask, how does the model change when you add that big loop? And to see how it changes, you basically ask, how does this sum over surfaces change when I put in this big defect? Okay, so the Yang-Mills model, in this kind of GUE version of Yang-Mills, you really, it really becomes exactly this sort of insertion cost story. You can see it very quickly and explicitly. Well, what turns out to happen, and this is in this big paper, and I won't really have time to say it very in detail here, is that if you switch to the Haar group, you can kind of extend the story. And one way to do it is to kind of get started is to imagine that you have some this sort of colored collection of edges, and you imagine that every edge you divide it into a million little tiny pieces, and each of those pieces is an identity plus a Gaussian. And then when you multiply them all together, you get something that's approximate. That's so it's identity plus a Gaussian times a Lie algebra element. And if you multiply them all together, you get something that's still very close to being in the Lie group. And so you can approximate a sort of something where you do a Brownian motion on the Lie group for some time by a product of Gaussian matrices. And then you can take a limit as that goes to infinity, you convert to the stationary distribution. And so we show is that just starting with Wick's formula and using this Gaussian approximation and taking limits, we can recover formulas that apply for these Haar matrix, Haar measure groups, like SUN and SON. So we were able to come with kind of a very different way of deriving this than was done in other places in the literature, which is to say, just start with Wick's formula, what we already showed you there, and just break your edge into pieces and use that as an approximation, and then you already have enough information to recover a random surface model that describes the Haar measure story.
This is arbitrary.
This is in arbitrary dimensions. So all of this works in any dimensions. Okay. But what happens is, this story, like I say, we did it for a bunch of loops. Yes, go ahead.
So based on the previous slide, do you expect that the Gaussian theory and the Haar theory end up being the same in the limit, or does someone have a guess?
So I don't really think so. I think that I mean there is a Gaussian theory to the if you have a strong enough, big enough beta, so if you have a very large beta, then you're going to get a Gaussian limit. So certainly the Gaussian field is one possible scaling limit. But once you get off of that, I mean, it seems to be that there's a lot of cancellation. In this UN model, you don't have the cancellation of this surface. Everything is sort of positive. Whereas in these other models that are related to this, these compact Lie groups, you get a lot of signs. And dealing with the cancellation of these signs is a big part of the battle, trying to understand what's going on there. And so my guess is that it's kind of a really qualitative different thing. I mean, it's sort of like if you want to compare the heat equation and Schrodinger's equation, you say, well, they're basically the same thing, right? You just put an I here somewhere, and so you now have some complex phase factors instead of just all being positive. But somehow, when you put it in, it kind of maybe changes the nature of the sort of limit you get. So our sort of hunch is that it's going to be a more significant departure. But yeah, no, it's a good question. Maybe, let me just say, the surface model, it is very interesting that we can describe, but it does have, these different sign factors that take some work to understand. And so right now, even, we're trying to use this to sort of show, you can rederive certain things about that in the small beta story about the area law and exponential decay. We can reprove these things in a surface point of view, but we're sort of kind of extending the set of places where you can prove things. So that we're extending the set of parameters. Let me say these are sort of our big goals. Discrete has one goal is we're kind of extending the set of places where we can prove this area law and exponential decay. We're expanding the set of beta and D for which this is possible, using the surface stories. Another stories we really want to kind of understand some sort of analog of what I call the surface tension that exists for the dimer model. We want to understand an analog for these models, and when it has a cusp, when it doesn't, there's a nice problem here. We would ultimately like to be able to use that construction to construct a continuum theory that looks Gaussian at small scales, but has these laws at large scales. This, by the way, big continuous task 1 is the one that wins you the $1 million. But honestly, you could probably get someone to give you $1 million for these others too, if you actually solve them. I mean, at least you'll get a nice job where they will pay you that much over a few years. So, all of these things are pretty exciting. This big continuous task 2, understand scaling of the model obtained when these things go to infinity together, and the lattice size goes to 0. This is where we sort of hope to make better connections to this, what we call Nouveau quantum gravity. That's a theory of random surfaces that we've had a lot of success in understanding in the last few decades. And so there's always been a sort of tantalizing idea that we might be able to connect this to a gauge theory more rigorously, at least in the big N goes to infinity limit. And so there's a big problem to try to figure out what kind of statements, meaningful statements you can make along those lines. And so this is homework or NSF proposal or whatever. This is something we would like to see happen in the future. And that's it. I'll end with that. Thank you.
Questions? So if you take the unitary group with a very large n, it should be closer to the Gaussian. Some sense.
I don't know. I mean, somehow.
Elements become.
The elements become approximately Gaussian. That's definitely true. Yeah. So if you look at projection onto P of the elements, they start to look Gaussian. But I guess the question is, what actually happens is Wilson loop trace expectations. Yeah, well, go ahead.
Yeah, a question and a comment. Maybe the comment first. You didn't say, or if you did, it was just very briefly normalization group, which is a way to answer some of these questions.
Renormalization group.
Yeah, so in the physics literature, obviously, it's very.
Yes. Yeah, that's right. And in fairness, the number of people who I did not properly reference in this talk is no, I mean even the number of people and the number of subjects I didn't reference
That's such a
is enormous. That's right. That's right. So so renormalization group, there's what I call perturbation theory. There's a lot of things people have done to try to make these things, it may not be quite math yet, right? Most of this yet, but it's
well, if there were one physics thing I would add to your talk, it's that one.
That one. Okay. Look into renormalization. Yeah.
But since on your last slide and certainly earlier when you talked about the diamond models, the surface tension seems to play an important role. Maybe you can say something more about it or go back to the slide.
Okay. Yes. So let's see, where was the surface? Oh no, I'm going the wrong direction. Okay, sorry. What just happened? Okay. Here we go. So I have to go back to some of these slides, like this one here. Yeah. So basically, there's a way to interpret the dimer model as a flow model, where you imagine from every black vertex you have a unit of charge flowing from the black to the white, and this flow will have approximately kind of be divergence free, because somehow in any sort of region you have the same number of black and white vertices, so the same amount of flow entering that region as leaving it.
Like you're trying to turn your configuration into a flow and so
yeah, so you could turn this configuration into a flow, and so if you choose a random configuration, that's sort of a random flow, and sort of in the limit you could think of it as a random divergence free flow. And what happens with a surface tension is that you find that maybe you want the limit to have a certain if you choose it randomly, probably the average flow is 0. But you can imagine something where maybe you're doing on the torus and you have a net average flow in one direction. That's quite large. Like if you had what they call the brickwork tiling, where every black vertex matches to a white one on its right, so everything is flowing to the right, then you'd have a lot of flow going in that direction. And it turns out for each particular average flow, there is sort of a maximal entropy Gibbs measure, the infinity that has sort of that average flow. And the sort of, if you want to have that average flow, what's the maximum entropy per site you can have? There will be some value for that. And that's what we call the surface tension. It takes you the average flow and it gives you this price. Well, you could imagine doing something similar for a random closed surface model, where each surface is orientable. So I think of the surface as sort of, if I give you a plaquette, I can think of it as sort of a, I think it's sort of a two form, if you like, a closed two form or something instead of a closed one form, and so I can imagine something where I have a whole bunch of surfaces that are all sort of oriented, so that this is the upside, this is the downside, and I have a stack of them like this, and that would give me sort of the average, an average two form of this type. And you can imagine that for each closed two form, each sort of constant closed two form, you could find what is the maximal entropy configuration that has this as its average, and so that would be like an analog of the surface tension for this model. And then you'd have to extend that to cases where you have maybe pluses and minus weights, but somehow you'd hope to get something like a surface tension. And so in the diagram model, whether the surface tension has a cusp or not, is really the heart of the matter. And that's what that's what determines whether it's in this exponential decay. I'm sorry?
Cost as a function.
Yeah, so what happens is that so I told you we have this set of possible flows. So that's going to be actually a two-dimensional space of possible flows. I tell you what the net flow is in this direction, and the net flow is in each of the two directions. And so I have this two-dimensional space of flows. And so as a function of that two-dimensional space, it could have a cusp at 0. This would correspond to the 0 flow. And if it has that cusp, then you're in the regime where you're in this massive case with exponential decay of correlations. And if you're in the if it's smooth, then you're in this other regime. And so so the belief is that the same story is going to apply in these higher dimensional settings where there will be something like a cusp but now it's a function of the space of constant 2 forms. So it'll be some higher dimensional space. It'll be a 4 choose 2 dimensional space, right? You have each of the 4 choose 2 possible and then you decide what's the net amount of surface you have in that direction, imbalanced, oriented one way versus the other. You see you're going to have like this 6 vector instead of a 2 vector, and you're going to assign a number to each of those things, and you're going to ask, does this function have a cusp at 0? And sort of our belief is that, that distinction, whether you have a cusp or not, also is related to this massive versus massless, exponential decay versus not exponential decay, area law versus not area law, the same sort of kind of duality, the same sort of dichotomy in this setting. And so what we would like to do is sort of kind of start proving statements like this in the simplest possible settings. So even if you can't do Yang-Mills on day 1, you can try to prove these similar statements for baby versions, toy versions, something where you can at least show that in these higher dimensional models, we do have behavior like what we expect to have.
Did you look it up for you?
So that is, yeah. So there definitely has been work on this abelian theory. I don't know if we've gone all the way to what I'm describing here, but yeah, so you can certainly do things with, U1, it's kind of a very simple group, and then your matrix, we're in sort of a weird world where some things are easier when n is infinity, some things are easier when n is 1. Some things, there are also people who do things on discrete groups, and in those cases, sometimes things are a lot easier because it's more like the Ising model, and some of the basic results you can easily prove for the Ising model, like the fact that you have this phase transition. You can prove analogs of that for discrete valued groups. But
Is there a review of the surface tension for the diamond model?
A review of the surface tension?
See if it
Yeah. Well, so if you just Google, so I know Rick Kenyon has written some nice survey papers on the diamond model. I don't know, Amal, what's the best recent survey on the diamond model?
But if you just go on surface tension, there's a survey of Rick called Lectures on Dimers that has a pretty detailed explanation of the surface tension.
Okay, Lectures on Dimers by Rick Kenyon,
Yeah.
Kenyon.
It's an old
paper. You can also read my old paper with Rick Kenyon and Andrea Luthoff. So we have a joint paper that's that talks about the dimer model and really kind of derives for general periodic weights what the formula for the surface tension is, and explains the meaning of these cusps and Arnott curves. We have a whole theory in a paper by the 3 of us. Yes.
What is the regular? So in the most basic Gaussian case, that's totally understood. What is the regularity of that random form?
So it turns out that in this Gaussian case, we understand it really is. You just take the regular Gaussian free field. So if you know what the Gaussian free field is, that's something it's a Gaussian field where you have logarithmic correlations. You know, so any Gaussian field is described by the point-to-point correlations, the 2-point correlation function. And here the correlation will be like the log of the distance between the 2 points, basically. In 2 dimensions, that's right. So in general dimensions, you'll have a Green's function. That's right. Some other things. That's right. So but it's kind of, I mean, you can also think of it as it's the standard Gaussian where your energy function is just the L2 norm of the gradient. So if you take that as your energy and then take e to the minus that and try to make that into a measure. So usually, you know, you take e to the minus an energy, and you can't do it because it's an infinite dimensional space and doesn't make sense. But in the case that this energy is a quadratic function, then these things always make perfect sense because it just defines for you a Hilbert space, and you can, you know, break it down. And it's just an independent Gaussian in each of the coordinate directions. So and so that gives you something we call the Gaussian free field. And so it turns out that you can also construct a connection, a Gaussian random connection. So if you have this Lie algebra, you can imagine it assigning like an independent Gaussian field for each coordinate, subject to the, you know, the constraints on Hermitianness or whatever. And so you kind of have a Lie algebra valued Gaussian free field. And then if you want to make a connection, you can imagine that for each of the coordinate directions, directed coordinate directions, you give an independent Lie algebra valued Gaussian free field.
So you're mimicking the construction of the GFF in basically on Lie algebra.
Yeah, so basically it's just the Lie algebra valued Gaussian field independent in each direction. And there is a, you know, all we care about in this thing is the, you know, is sort of the product around closed loops. So in some sense, you know, you can project onto the set of, you know, you can mod out by the things that assign 0 to closed loops, right? So so you know, you can mod out by that, but anyhow, what you get when you do that is just exactly this Gaussian connection. You can project it onto the.
So would its regularity be the same as the GFF?
Exactly, yeah. So it's just the same as the Gaussian free field. But then you have to ask things about like, well, what about when I take, you know, the product around a large loop, and so, you know, Gaussian field, you can't really integrate it along a line in 3 dimensions or 4 dimensions. You integrate it around something else. Yeah, but yeah, that's basically the answer.